So now if I want to find out the value of shear stress at the top of flange, then I have to take y is equal to d by 2. And when I will take y is equal to d by 2 and put the value in the equation, I achieve tau is equal to 0. So at this top edge, the value of shear stress is 0. Now let us come to the point. Next one. Now for the lower edge of the flange, y is equal to small d by 2. Now if we have to put the value small d by 2 over here, and then by putting all the values of capital D, small d, f and I in this equation, we can achieve the answer. But let us be understood over here. Please refer. At this age, I want to find out the value answer. At this age, the y is equal to small d by 2, as this 310 is small d and small d by 2 is nothing but 310 by 2, and this value we have to put in this equation, while capital D is equal to 350 mm. So please refer the PPT. Then tau is equal to f over 8i. Why 8i? By taking the 4 which is taken as out of the bracket, so 4 into 2 8i. So 40,000 divided by 8i, I value we have already been found out in the previous problem, because the same problem which has been given to over here. Capital D square, that is 350 square minus 310 square, we achieve the answer 0.7 megapascal. So this is the value of shear stress at the junction of a flange and a web. So this value, and this value is equal to 0.7. Similarly, at the bottom side, this is also 0.7 megapascal, as the given section is of symmetrical I section. Now, second portion, shear stress distribution in the web. As discussed in the previous problem, and we found out that the maximum shear stress taking care at the neutral axis, and the value is we found out as 13.06 megapascal. Right now the intention is the shear stress at the junction of web and flange. We haven't found out the value junction between flange and web. Now at the junction of web and flange, the value of tau which has been given by f into capital B into bracket capital D square minus a small d square divided by 8IB. By putting all these values, that is F is equal to 40 kilonewton in converted in terms of the Newton, 40,000 Newton. Capital B, that is the width of a flange or section, that is 150. D, capital D, that is 350. Small d, that is 310. I value we have found out already, 8 is the constant and small b is the 10 value. We found out it is 10.51 megapascal, the value of tau which has been taken care at a junction. Alternatively, we can find out same by multiplying capital B by small b to the 0.7. So finally, if you refer over here, this value, I will take another page right now. This is our diagram. And this is our section. Now, this value which is known to us as 0.7. Intention is to find out this value, and that value which has been found out by capital B by small b into 0.7, or use direct the formula. The capital B, that is 150, the small b, that is given as 10 into 0.7, and we found out as 10.51. So all the necessary values we have been found out to plot a figure. So if you refer, this is our shear stress distribution diagram. So the shear stress distribution, which is symmetrical about neutral axis, and it is plotted as shown in this figure, and just see that the value of shear stress suddenly changes from 0.7 to 10.5 at the junction of flange and the web. Suddenly changes. Now the second part, that is our intention is to find out the total shear carried by the web. What will be the total shear force carried by the web, and what is the remaining amount which will be carried by the two different flanges? Obviously you can visualize over here from the figure that the majority shear force will be resisted by this web only. Very smaller amount, just visualize 0 and 0.7 up to and parabolic nature. So this much variation, this much value will be resisted by this flange, this much value is resisted by this flange, and huge large amount of shear force will be resisted by the web, and intention is to find out that value. So total shear force carried by the web will be equal to the total shear force carried by I section minus the total shear force carried by the two flanges. Interesting point. I want to find out the shear force carried by the web, and that is equal to the total shear force minus twice the shear force resisted by the flange. The same thing which has been written over here. Total shear force carried by I section minus the 2 times the shear force carried by the one flange. So 40,000 in terms of the Newton minus 2 into shear force carried by the one flange. So what is the intention right now? Let us find out what will be the shear force carried by the one flange. Now to find out the shear force carried by one flange, first calculate the shear stress in the flange at a distance y from the neutral axis. We have to find out the shear stress in the flange at a distance y from the neutral axis at any one layer above the web. So for that, let's consider an elemental strip of flange of thickness dy. It is understood over here in this figure on this tabletop. This is my neutral axis. Consider one elemental strip in the flange. One strip having a thickness dy. The thickness of this strip is dy. So now let us go ahead. For that, area of strip is equal to width of a flange multiplied by the thickness of strip. Now width of flange, as we know, that is 150, thickness of strip, that is dy. So shear force carried by elemental strip is equal to shear stress at a distance y in the flange multiplied by the area of strip. So shear stress at a distance y in the flange multiply by the area of strip. Area of strip, it is known to us, that is dA, that is 150 into dy. Intention is to now find out the shear stress at distance y in the flange. Now, shear force carried by the elemental strip is equal to tau multiplied by 150 into dy. Tau, that is the shear stress in the flange at distance y from the neutral axis. Now, total shear force is obtained by integrating the above equation from 310 by 2 to 350 by 2. These two ranges. Why these two ranges? Please refer the figure on this. This is my I section. This is one layer. This is my neutral axis. From neutral axis, I have to take the value of y. This available value is 310 by 2. This depth is available 350 by 2. So now this y ranges from this value to this value. Hence, we have to integrate the value between the range of 310 by 2 to 350 by 2. So, the total shear force carried by one flange is equal to integration of 155 to 175 tau into 150 dy. Now, we already know the value of tau in the flange distance y from the neutral axis is given by an equation Fa y bar by Ib, where F is known to us, that is a 40,000 Newton. Now, intention is to find out Ay bar. Ay bar is nothing but moment of area of flange above y from the neutral axis. So, first area. Area is nothing but B bracket D by 2 minus y into half of bracket capital D by 2 plus y. Means what? I have to find out the area first. So, area which has been found out from here, that is the area of flange, multiply by the distance of the CG of the area to the neutral axis, we have to find out. So, for a particular strip, we have to find out, and hence we found out it is B bracket D by 2 minus y into half of D by 2 plus y. Why this statement? Because y is nothing but this distance. So, this is capital B. This is D by 2. So, area available is above this line, above this small strip, that is B bracket D by 2 minus y. Now, this is the area. Now y bar. Y bar is nothing but the CG of this area to the neutral axis, and that is half of the depth, that is D by 2 minus y. This is small portion plus y, and by simplifying this we can get it is half of D by 2 plus y, and the same thing which has been shown over here on this PPT. So now B is equal to 150, capital D is of 350, y, that is the part, because we have to find out variation with respect to y, into half of 350 by 2 plus y. Let us simplify this equation and we get ay bar is equal to 75 bracket 175 square minus y square, and hence ay bar is equal to 75 bracket 30625 minus y square. The value of I we had already been known to us from the previous problem, and width of flange B. Here the B is nothing but the width of flange because the strip which has been taken care in the flange portion, that is of 150 mm. So substituting all these values, the tau is equal to 40,000 multiplied by 75 bracket 30625 minus y square divided by the I and B value. So tau which is comes in the proportion with the y square. So tau is equal to 0.00011 into bracket 30625 minus y square. Now substituting this value of tau in the equation of total shear, because the total shear value, intention is to find out the total shear force, and we know that it is nothing but the integration of 155 to 175 tau 150 dy. The value of tau we have been found out in terms of the y square, 0.00011 bracket 30625 minus y square. This is the value of tau into 150 dy. Now in this case 0.00011 into 150 is a constant term which comes out of the integration sign, and remaining portion, that is integration of 155 to 175 bracket 30625 minus y square into dy. Simplifying once again by carry out integrations, 0.16 bracket 30625 y minus y cube by 3. The range is of 155 to 175, and please perform this very simple integration procedure because this is the y. So bracket 175 minus 155 minus 1/3 of 175 cube minus 155 cube. Solved simply using your calculator, and we found out 1070.6 Newton. This is the shear force